Okay. So today talk about singularity of pairs and log-canonical thresholds. So the goal today is to prove Minkowski-Mining theorem. So what we need to link two things: not a finite inequality to some bounds on multiplicity. Okay, and we're going to use two ingredients here to do this step. One is inversion of adjunction. And the other is log-canonical thresholds. Okay. So let's see how these things come in. So let me start 4.1 with log discrepancies. So you want to think about log discrepancies as a way of measuring singularities of divisors on varieties, or more generally, or subschemes on varieties. And for simplicity, I'm going to just focus on the case when the variety is smooth. So I fix X to be a smooth variety. Okay, so all these definitions can be given more generally, and it's interesting to give them, allow singularities for instance, from the point of view of the minimum model program. But for today, for these lectures, for this problem, we only care about smooth varieties, so we focus on that case. So let me first introduce the following terminology. I divisor E over X. What is it? It's a prime divisor, E, which live on some model Y with a map down to X, where F is a proper birational morphism, and Y is, maybe we can assume to be some smooth variety. So think about a resolution. Of course, X is already smooth, but I can blow up further. And when you blow up, you extract more divisors. So every divisor you can extract in this process is called a divisor over X. So it has a center, which I denote by Cx of E in X, which is just the image of the divisor inside X. And then we say that A is exceptional over X if the codimension of the center in X is at least 2. Okay, so the usual terminology. So the idea is that I don't want to have to pick a model Y every time, but just talk about divisors over X. And the key point is that I don't really care about even the choice of a model, because you can blow up further and so on, and maybe you look at the same divisors up to some equivalence. So what you really care about is divisors. So if E is a divisor over X, then this defines a valuation. Order E on X. In fact, it's a valuation of the function field of X. And the center of the valuation is precisely the center of E, I mean the generic part of the center of E. So the way you do it is that if I can evaluate, I can apply evaluation to any ideal shift, maybe let's say a non-zero ideal shift inside on X, and I can define what is the order of A. By what I do is that I take A, I pull it back to Y, and then I localize at E. So this thing here is a DVR. And then it has a valuation, which is the order of vanishing along E. So this defines a valuation of X. That's what we mean by valuation of X. Okay, so what I really care here is divisors. I really care about this valuation. These are called divisor evaluations. And So if I blow up further and take the proper transform of divisor E on a higher model, I will define the same valuation. So I don't really care much about which choice of Y I get. So sometimes I'm going to assume that maybe Y is higher than I first assumed. So also, just for notation, if I pick a rational number Q, then I can define the order of A to the R. So this, you think about this as a formal expression. If R is an integer, is a positive integer, then it's really, this is just the power of A. It's consistent with that. And the way you define this, you just pull out the R as a rescaling. So I can do that. Okay, so sometimes I refer to A to the R as a Q ideal. Okay. So yeah, so let me tell you now what is a pair. A pair for us consists of a variety X, which I assume it to be smooth, and Z. What is Z? Z is a formal linear combination of closed-up schemes. It is a finite linear combination of closed-up scheme. So here, so this is called a Q scheme. So where Zi inside X are closed subschemes, and the Ci are rational numbers. Okay, so an example is you take X and delta, where delta is a Q divisor. Again, X is smooth, so a divisor can be regarded as a veil or Cartier divisor, so I can regard delta as a Q scheme. Also, sometimes I'm going to write maybe something X to the A to the R to mean X and then R times the scheme defined by A. Okay, and sometimes maybe say X maybe is a spec of R, and then I allow the notation A to the R, where A is just an ideal inside R, maybe non-zero. So I'm gonna switch from one notation to the other, but the main concept is this: you have a variety, and then you have this linear combination of closed-up schemes.
Tommaso,
Yes.
the ZIs are all of the same dimension, or it is not necessary?
No. I'm not assuming anything about the Zi. Okay. They could be very complicated.
Okay, thank you.
Yeah, they could be different dimensions. They could have embedded points and so on. And so we say that a pair XZ is effective if all the coefficients are positive, non-negative. Like a divisor is effective if all the coefficients are non-negative. So another definition I want to give is what is a log resolution. So log resolution of a pair XC is what? Is a proper irrational morphism F from some variety Y to X, where Y is a smooth variety, such that, and then I want to have, so the exceptional locus of F and the inverse image as a scheme of each Zi, I want this to be a Cartier divisor, So in particular, this will factor to the blow up of each individual scheme. And then I want the sum of these things, as the sum of these divisors, to have simple normal crossing. So simple normal crossing, it just means that locally, it looks like a coordinate either planes. Or another way of saying this is in some local coordinates is defined by monomial equation. Okay, so that's what a log resolution is. And I'm going to use the following notation. I'm going to write F inverse of Z to be the following Q divisor. So you know that this is a Q divisor now. So what I do is I think about, again, maybe there's only one Zi as a single Zi. What I do is you blow up that Zi so it becomes a divisor. But then this divisor could be very complicated. And the variety could be singular. And then you resolve the singularities and you make everything in simple number crossing. Okay. So let me know if there is any questions about the definitions. So the next definition is, suppose I give you E as the divisor over X. And then suppose I give you a pair on X. And say the E lies on some, it doesn't matter which model I pick, but say there is some model which E lies on. So now I want to define a log discrepancy of the pair along E or E over the pair. So the definition, it is denoted by the following symbol, is A, E of X comma Z. So this is a difference between two numbers. The first one is I look at the order along E of ky over x. So you think about this as a Jacobian, and I add 1 to it. That's where the word log come in. And then I subtract the order along E of Z. So let me maybe just say what this is. Again, this is an exception divisor, which is linear equivalent to ky minus the putback of kx. And since x is smooth, that's the same thing as being the divisor defined by Jacobian of f. This one is just simply the sum of the Ci times the order of the deal of Ci. Okay, so the order of the subscheme. So just extended by linearity. Okay. Okay, so this is what the log discrepancy is. And now we say that the pair Z xz is, and let me introduce a few terms, terminal, canonical, KLT, which stands for the Karamata log terminal, and log canonical. If what? And now there are some conditions on discrepancies. For terminal and canonical, I'm looking at the following condition. The discrepancy of the pair here is going to be greater or equal than 1 for all E exceptional over X. And the next one will be greater, sorry, I got the first one wrong. The first one is strictly greater than 1, and then going to be greater or equal than 1 for E exception of X. And then KLT, you ask the discrepancy is greater than 0, and log canonical is greater or equal than 0, but now you're asking this for every E over X, so I also allow divisors on X. Okay. So it takes some time to absorb what this definition are saying. So I'm not going to try to do this in this lecture. Typically just work with this thing, with this notion for a little while, and then you get a better sense of it. But let me just say maybe a couple of words about, so canonical, we already seen it. The condition already came up in the notifier inequality. Terminal is the one that's closest to smooth. For instance, on surfaces, if you take Z to be 0, the terminal is the same as smooth. And terminal is a singularity you're going to pick up in a minimal model if you just run the minimal model in a higher dimension. And canonical will be the singularity in the canonical model. And then log terminal and log canonical, more precise, Karamata log terminal and log canonical, those are conditions that come when you don't just look with you don't care just about a variety, but you care about a variety with a boundary divisor, and that become very natural notions there. Okay. Anyway, so the further down you go in this sense, the more singular the more singularities you allow, and this is kind of the limit to which you can go, because as soon as you go to a negative number, as soon as you allow all discriminant to be negative, then you can show that in fact those will go to minus infinity. Okay. So a key statement here is the following. So this is inversion of adjunction. I mean, inversion of adjunction is a very rich topic of research. There are many things unknown, many things are not known. I'm gonna just explain one important case that is known, which is the following. So this is kind of a bit of a technical statement. Let's see. So you start with x comma z to be an effective pairs. And now you're gonna take h inside x to be a smooth divisor, smooth and reducible, say, prime divisor. And assume that h is not contained in support of z. The support of z is just a union of the support of zi's. Okay. Now assume the resistance divisor E exceptional over X. I mean, it's not really important. This is but anyway, so the or maybe, I mean, maybe remove this exception and just say, so E over X is E different from H. In a sense that any proper transform of H on any model. Such that if I call W the center of E intersect H is not empty, and the log discrepancy of xz plus H is less or equal than 0. So if I add H to the pair, then this becomes a no log terminal, non-chromatic log terminal along E. Then the resistance divisor F over H such that the intersection with this cycle, with this set W is not empty, the center, and the low discrepancy, it's the interesting part, of H and 0 restricted to H is also non-negative. So maybe I should say 0 restricted to H is a pair, is a skew scheme in H, which is just given by the same coefficient, and then I just restrict every Zi intersect with the H. So I regard it as a skew scheme on H. Again, this is is a bit technical. If it's the first time you see these things, it's not clear what I'm doing. But maybe the proof will actually give an idea of what is interesting about the statement. So let me sketch the proof. Let's prove it. Okay. So say, so I assume that E is a divisor on Y over X where this is the log resolution of the pair x, z plus h. Okay, I'm gonna let h prime inside y be the proper transform of h. So maybe I can draw a picture here. Let's see. So this is y with a map down to x. So this is the divisor h. It's a step down view, and I have the proper transform here. And then another question is, where is E? So there are two cases. Maybe the first case is that E intersect H. Okay. So the easy case is that E intersect H prime in the log resolution. Now in this case, what you're going to do is you're going to let F be a reducible component of this intersection. So in my picture, F will be this guy. Okay, and now you use adjunction. So adjunction formula, let me just write it with the canonical divisors. For suitable choice of canonical divisors, if all the canonical divisors are chosen compatibly, then it can be written in this way as an equation of divisors. So again, I'm restricting to a smooth divisor H prime on Y, and I computed the canonical divisor on H prime in this way. Similarly, on H, I compute the canonical divisor starting from kx plus h restricted to h. I just need to arrange so that the restriction is well defined as a restriction of divisors. And then another thing I know, because I'm doing this on a log resolution, is that the order along f of 0 restricted to h will be equal to the order along e of z. So when I put these things together, I'm claiming that this implies that the law discrepancy at f of h comma z restricted to h will be equal to the log discrepancies at e of x z plus h. So you just need to put the pieces together, compute these relative canonical divisors. You see, from here I compute the relative canonical divisor for this guy. On this side, I compute the relative canonical divisor for this guy. And then I add 1 on both sides. I subtract these quantities on both sides. So far I have everything equal. Now you say, why do I have an h here? Well, the point is that this h takes care of the difference between taking a proper transform of h and taking a pullback of h. The difference along E and F will be exactly this vanishing order. Okay. So if you put it together, you get this equality. In particular, the right-hand side is less or equal than 0, so the other one is less or equal than 0. So this is just an adjunction formula applied on below and above and compared. So now, what is the hard case? The hard case is when E intersect H is actually empty. So now I need to be a little bit more careful. Picture. So X is here, this is Y. Now what do I have? We have, here was H, and there was this set here, W. So here I have the proper transform H, for H prime. And maybe now the divisor E is there. Okay, so now how do we do? How can we compare these two discrepancies, log discrepancies? I feel like there's no way of doing that. But here's a magic thing. So I'm gonna write, oops. Look at ky over x, and then you subtract the pullback inverse image of. So this is just an equation of divisors now on a log resolution. So these are Q divisors. What I'm gonna do is gonna round up all the coefficients. So this is a component-wise round up for the coefficients. And then whatever it is, I'm gonna write it as a positive part minus a negative part. So now P and N are effective with no common components. Okay, so and now there is this important theorem, is called the Sokurov-Kolar connectedness theorem. Which says the following thing. So you look at the negative part in this divisor. So you look at N, you look at the support of N. And then, so this sits inside Y, right? So in the F induces a map from the support of N to X. And the statement is that this map has connected fibers. Okay. Okay, so why do we need that? The point is that I'm looking at this set W over here. And what I'm gonna do is I look at the, pick a point, maybe, okay, let me have to do this way. Pick a point here, X, and look at the fiber over this point. So this will be F inverse of X. So I'm gonna pick X inside W and look at the fiber. So this fiber meets both H prime and E. And you notice that H prime and E are both contained into the support of N. So by connectedness, there exists another divisor, E prime, in the support inside as a irreducible component of N, such that E prime intersect H prime is not empty, right? So the point is that there's going to be some other divisor. There may be some bunch of divisors here, and I can find one here, E prime, and this E prime will intersect H. But now the question is, what does it mean that there is in the support of N? Well, again, first time you see these things, you don't see this immediately. But if you just stare to this condition here and look, what does it mean for the coefficient there to be negative after round up? It means that the coefficient has to be strictly less than 1. Sorry, it has to be less or equal than -1. But then you add 1 to it. Sorry. So this means, so the fact that E in a reducible component, E prime of N, this precisely means that the discrepancy of the pair X, Z plus H along E prime is still less or equal than 0. So this only works exactly at this point 0, at this value 0, the log discrepancy. So it reduces to the easy case. What it says is that the regional divisor we had was too far away in the resolution to be able to say anything about to apply a junction. But even though that one is too far away, I can find another one which actually meets H prime. And after I have that divisor, then I can do a junction and come to the conclusion. So the way you want to think about this, we're going to apply, I think we become more clear how to use, how to think about this result when we actually start using it. But the idea, what it says is that if you have a pair and you want to quantify singularities with this terminology, like being log-canonical, being non-log-canonical, being not KLT, or this kind of conditions, then what it says is that if you have a pair which is singular enough on X, and then you restrict to an hyperplane H, then as long as you can ensure this condition of discrepancies, then after restriction, the pair is still singular. Singularity will not improve. Any questions on this?
Okay.
Yes. No. Other question? No. Okay. So, for instance, as an application of this, we're going to use the following proposition. Suppose I start with X delta, an effective pair. So now delta is a Q divisor. And assume there is an exceptional divisor E over X such that the dot discrep of X delta along E is less or equal than 1. So in particular, the pair is not terminal. Okay. So I'm going to let T be the center in X of E. Then the multiplicity along T of delta, which is defined linearly, is at least one. So maybe you should say A. T by definition is, so if delta is just a sum of di, then this multiplicity will be just the sum of the di times the multiplicity of the individual character divisors. Okay. So the idea of the proof is that you cut down to a curve. So when you cut down, first you cut down until the dimension of T is 0. And for this, the singularities remain the same by some sort of Bertini argument, just because the proper transform will always intersect the exception divisor until I get to something dimension 0. Then you cut down one more time. One more time. At the point P, now T is just a one-dimensional thing. And then you get to a pair with low discrepancy, some low discrepancy, which now become less or equal than 0. And then eventually you reduce to a non-KLT pair on a curve. But the non-KLT pair on a curve is the same as the coefficients of the divisor to be at least 1. And that's where the multiplicity comes in. I'm going to skip the details of this. I'm sorry, maybe I should have given more rigorous proof. It is in the notes, but let me move on. I think it's more interesting to see application of this theorem later. We are going to apply it on in the Poole-Vygotsky mining theorem, and then that I will do this carefully.
Also,
Yes.
just a question. Am I wrong, but this says that T is in the support of delta?
Yes, because X is a smooth variety. So all the statements here, now for this statement, I need X to be smooth. So if the dot discrepancy of E is less or equal than 1, and E is exceptional, then it has to be in the support of delta. In fact, if you like, the statement in particular will imply that.
Okay.
Yeah.
Thanks.
Yeah. So it's important here that E is an exception divisor. Yeah. Anyway, so don't worry too much about this proof. I want to focus more on what I'm going to say next. So I'm going to use this inversion of adjunction later again, and I'm going to do this with all the details to see how we apply it in kind of situation like this. And then you can fill in the details on this proof. But I want to talk about the second ingredient here, which is log-canonical thresholds. Okay. So let me give a definition. Again, suppose X is a smooth variety. So I suppose that I pick A, an ideal sheaf inside X, which is non-zero. So I want to define a log-canonical threshold defined by LCT of A. By definition is what? Is a sup of the numbers T such that if I look at the pair X, comma A to the T is log-canonical. If A is a unit ideal, then the sup will be infinity. But otherwise, at some point, I'm going to get a finite number. Okay. So if Z is, I said, X is a closed-up scheme, then I denote the log-canonical threshold of X. I can also write in this way, X in Z. In this case, I need to write X because when I write A, I'm also remembering X. But if I write just Z, I need to remember also the ambient variety X. And this is just a sup, it's just, if you like, the log-canonical threshold of the ideal of Z. Sometimes it's useful to have a local condition. So if I pick a point in X, close or not, I can also define log-canonical threshold at the point of a pair XC. Has to be a log-canonical threshold of the ideal Z inside the local ring. Okay, so this means that you just look at log-canonical threshold in a neighborhood of little x. And if followed by definition, I see the log-canonical threshold of an ideal A is the same as the infimum of what? Over all E's, prime divisors over X, of what? You look at the order along E of, well, every E will come with some Y, look at a reticle divisor plus 1, divided by the order of E. This is just because the log discrepancy of x a to the t is equal to this order E, okay, y over x plus 1 minus t times the order of E and then the definition of A. Okay, so if I just solve for t, I get that fraction. If I put that equal to 0 and I solve for t, the condition that is equal to 0 is a condition relating to the definition of being log-canonical. So this pairs fail to be log-canonical if I can find that E for that this log discrepancy is negative. And then, so the threshold is 0, and that's exactly what that fraction where the fraction comes from. And in fact, this is actually, one can actually show that this is a minimum if A is not a unit ideal. Can be computed from the log resolution. Okay, so let me give an example. Let me give you the following example. So suppose that X is a affine space. So A now is a non-zero ideal inside the polynomial ring denoted by R in n variable. Okay, and now to A we associated, you remember probably, the Newton polyhedral P of A inside the octant. And I just recall you what this is. Maybe I draw a picture. So now I'm not assuming that A is n primary. So in general, this thing will not cut out a bounded region, but maybe we cut out something that looks something like that. Okay. So P of A is a region above this polygon that I draw, and so basically is a convex hull of all the points U that are exponents of monomials in A. Now what I'm going to do is that I look at the vector 1, 1, 1, 1. So this is the vector E. So I'm going to let E be the vector 1 to there. Okay. So then I'm claiming the log-canonical threshold of A is equal to the sup of the values t such that E does not belong to the rescaling of the PA by t, which is the same thing as saying is the sup of t such that 1 over TE does not belong to PA. So what I'm going to do is that I rescale this vector until it hits the boundary of the Newton polygon. Okay. And that number, the coordinates of this point intersecting this line, if I call this coordinate lambda, this is exactly 1 over the log-canonical threshold of A. Okay. So let me give a concrete example, which is kind of the main example for us anyway. Suppose that A is a diagonal ideal, x1 to the d1, all the way to xn to the dn. So the picture here now becomes, so do something like this. So this is the Newton polygon, PA. So this is the point D1, we call it D1. The last one is the point of coordinate Dn. And now we are looking about the coordinate of this point here. So how do you compute those coordinates? Well, the point is that the equation here, the equation of this hyperplane, or this face, is given by the sum of the ui over di equal to 1, right? Because you just said all the u1 equal to d1 and the other one 0, and you get exactly 1, so it's satisfied. So you get interpretation of the points. So if I call this number lambda, what I see is that the point of coordinate lambda will lie on this hyperplane. We satisfy this this equation. Okay. But now, if I divide by lambda, I see that 1 over d1 all the way to 1 plus dn will be equal to 1 over lambda. But as I just told you by the formula before, this is the same thing as a log-canonical threshold of A. So this gives a formula for a log-canonical threshold of A. So in general, if I look at this, so this ray will intersect the Newton polygon along some facet, some face. And the face will have some equation. So the equation of this face will be the sum of ui. Let me write in. We write in this way: ai ui equal to 1. Where now the coordinates is 1 over a1, 1 over an. And then we see that this log-canonical threshold, I write it here, and the log-canonical threshold of A will be just the sum of the AI. Okay, by the same argument. The point is that this AI now, they are in general rational numbers. Even 1 over AI might be rational numbers. I'm not assuming that those are lattice points on the axis. Okay. So let me just give an idea of the proof. I'm going to skip the details. So you look at AN, you think about this as a toric variety. And so you think about everything happening here, you think about the Newton polygon to be inside an R, where N is a lattice, I denote by N the lattice Z to the N. And then I take M to be the dual lattice. It's also isomorphic to Z to the N. So now, if I have a E, some toric invariant divisor over X, so what I mean by that is that, first of all, I know that if the ideal is monomial, then it's invariant under the torus action. If X is a toric variety and the ideal is invariant under the torus action, I can take a log resolution, which is toric invariant. It's a equivariant resolution. Therefore, I can, in order to compute log-canonical threshold, I can just, it suffice to check this on toric invariant divisors over X. So you think about monomial evaluation. So this corresponds to some point in the dual lattice. In fact, with integral, in fact, is inside the non-negative part of this dual lattice. And now I know what is the order along E or on some monomial. Well, that will be just the pairing between U and V. So in particular, the order along E over the ideal A will be the minimum of the pairing between U and V, where U is a point in the Newton polygon of A. Now, not a lattice point anymore. On the other hand, I want to know the discrepancy. So I need to understand what is this quantity. turns out that this is computed by pairing V with this vector 1, 1, 1, 1. And this follows that if X is a toric variety, then the canonical class of X is linearly equivalent to minus the sum of the toric invariant divisors on X. So this is a toric invariant prime divisors on X. So what you need to do is that you want to find a log resolution will be corresponds to taking a subdivision like of the fan, which is this octant you start with, where the Newton polygon is. You subdivide that. And every time you subdivide, you're introducing a new toric invariant prime divisors. And then you compare the canonical divisors using this formula. And then it's easy to see that that's what you get. So in the end, you see the log-canonical threshold of A is a sup of all the T's such that EV is greater or equal than TU, comma V for all V inside the duo, in the projected part of the duo, which is a primitive element. So these are the ones that correspond to prime exception divisors. Primitive, let me write this better. Okay, so and then once you have this condition, then you interpret this as a condition of lying. There's a scaling of V of E lying inside. I can bring the T on the other side, and we become one or either way you want to see it. Okay, so now we come. Any questions on this? So let me go back maybe to the statement here. So let me just look at the statement again. I have an idea A, and I look at this Newton polyhedron, and I look at the vector coordinate 1, 1, 1, and then I just rescale it until I hit the polyhedron. And then that rescaling factor is a reciprocal of the log-canonical threshold. And in particular, if I write the equation for an hyperplane, of the hyperplane supporting this face, and this is the equation, then I get an explicit formula for a log-canonical threshold. So it's very useful. Now we're going to use that in the proof of our next theorem. So the next theorem is due to Corti, and n is equal to 2. And then, in fact, it's a theorem of mine with Ein and Mustaz in general. So let me give a setting first. Again, suppose X is a smooth variety. And R, let me denote by R the local ring or at some point. So a local ring on X. X, and by M it would be the maximum ideal. And now I'm gonna pick A inside R, be an M primary ideal. Okay, then we have the following formulas. The first one is about the length. If I look at the length of R mod A, this I can bound this below by 1 over n factorial times n to the n over the log-canonical threshold of A to the n. And the second is that I can do the same thing for the multiplicity of A, and that will be equal than, it's the same expression minus this factorial. Okay. So the way you want to think about this is that the log-canonical threshold is this invariant of singularities related to pairs, you know, canonical or canonical, these sort of things. The most singular a pair is, the smaller the log-canonical threshold is. So it's kind of go the opposite direction. So if you have a pair which is very singular, the log-canonical threshold is very small, but then it means that this fraction is very large. And this will put a bound, a lower bound on the multiplicity. And that's exactly the link that we needed to go from singularity of pairs to multiplicity. And you see the two theorems we are proving here. The first one goes from, it allows you to go from something like a canonical singularities or non-canonical singularities to non-log canonical singularities. Once you have that step, then this inequality it goes from the log canonical threshold to multiplicity. So let me explain this, where this formula coming from. So first, it's easy to see that 1 implies 2 using two things. Well, remember that first of all, the sign multiplicity is a limit of the length of powers of A over m to the n, and then there is a scaling factor, 1 over n factorial, when m goes to infinity. And the log canonical threshold, let me write it in this way, of A can be compared, maybe this is a silly way of writing, so let me write it this way. If I take a and take a power of A, then it's kind of clear from the definition that that's the same thing as 1 over n times the log canonical threshold of A. So in particular, when you look at the formula here, this quantity I can approximate by these quantities, right? But of course, the n factorial will be taken care of by this condition, by this coefficient. The question is, what happened to this one? Well, this one is going to come up exactly from here when I take this power from this coefficient, so they cancel out. So if you just put it together, apply 1 to powers of A, and then take a limit, and then you get 2. So that's we need to show. We need to prove 1. So here I have an arbitrary variety, and then I look at the local ring. So this is not a fine space, but I can make some reductions. So the first reduction I want to do is to the case when this ring is a polynomial ring, or if you like, a localization of the polynomial ring at the maximum ideal at the origin. And the second reduction is when A inside R is a monomial ideal. So let me maybe explain the second reduction. For 2, so we use a flat degeneration to monomial ideals. Because it's flat, this preserves length. Okay. So how do you degenerate an ideal in a polynomial ring to a monomial ideal? Well, what you do is you fix a monomial order, and then you start acting with C star, and you degenerate, sending the parameter of the action added to 0 to infinity, and that goes to the ideal A with the generator initial ideal A, which is a monomial ideal now. And that is the generation, so the generation is parameterized over A1. Away from 0, all these ideals are isomorphic. It's like the generation to the tangent cone, if you like. Before I get to a tangent cone, everything is isomorphic. At the end, it becomes a cone, so it's become homogeneous. In this case, we make it actually monomial. With a monomial order, you get a monomial idea. So this keeps track, it says that under this degeneration, this part of the equation remains the same. But we need to worry also about this part in order to lift the property from the monomial case back to the original situation. And for that, we use a property of log-canonical threshold, and then use this and something called semi-continuity of log-canonical thresholds. Which essentially says that the log-canonical threshold at the limit of the initial ideal will be less or equal than the log-canonical threshold of A. So the singularity cannot improve under specialization. That's what this statement says. So with this inequality and the fact that lengths remain the same, if you prove the bound in the monomial case, then you can deduce the bound before the generation. So with these two reduction, so let me assume A inside this polynomial ring is monomial ideal. Okay, and now we have formulas. We work hard for this formula. So we have formula for the log-canonical threshold of A. So let me maybe draw a picture first. And draw this picture again. So again, what I do is that we look at this vector where it hits this cone. Well, there was lambda in the picture before. I look at the supporting hyperplane for this face. So here I have the point lambda E, and the supporting hyperplane has equation. I'm going to write AI UI equal to 1. So the intersection here is 1 over A1, 1 over AN. And now we have estimates. We have a formula for the log-canonical threshold. So the log-canonical threshold of A is just the sum of this coefficient AI. And the sign multiplicity of, sorry, no, I'm doing the length. And the length of R mod A is greater or equal, we proved this last time, of this quantity. In fact, this inequality we actually proved. We argued for that inequality. Okay, so now we want to compare. And now what you do is that you're going to use the fact that the geometric mean is always bounded about by the arithmetic mean. So here I'm doing the geometric mean and arithmetic mean of these coefficients AI. So what does it say? The geometric mean is a product of the AI to the 1 over n. This is less or equal than the sum of the AI divided by n. Okay, so now using these formulas, we just combine them, and we see the length of R mod A. Well, this is greater or equal than 1 over n factorial times the product of the AI. Sorry, there was a mistake here. This is a product of this coefficient, which are 1 over AI. Okay, so is what? I'm going to write this in the following way: 1 over the product of the AI in the denominator. But now using this inequality between the means, I see that this is greater or equal than 1 over n factorial. And what we have, the reciprocal of that is n over the sum of the AI. But now I'm taking an nth power of that. So here we have it. This is 1 over n to the n over the log-canonical threshold of A. Yeah. Okay, so this finishes the proof. Any questions on this proof? On the statement?
So, what happens if the if this ray intersects the Newton polygon at the corner?
Yeah, that's certainly possible. Then you can just pick. You can pick either of the. Let's say maybe in this picture you can pick either faces, or you just pick any plane, any hyperplane which is gonna go through that point, and it does not intersect the interior of the polygon, of the Newton polygon.
I see.
The Newton polygon is convex by construction, so I can always find one that is anyone will do.
Okay. Okay. Thanks.
Okay, so I think we're doing well on time. So now we have everything in place to prove this theorem of Minkowski-Manning. So here's the theorem. So every x4 inside P4, smooth quartic threefold is birational super rigid. Okay, so let's prove this. So first, let me make a remark. First note, so the Picard group of X is actually generated by the hyperplane class because of Lefschetz. Lefschetz hyperplane theorem will tell us that. And also, the anti-canonical class of X is linear equivalent to this hyperplane class. And this is by junction. And from the canonical class of P4, using a junction, we can compute Kx. So the first thing I want to say here is that it is a Fano Picard number 1, so it is a Maury-Faber space. So the question whether is birational super rigid makes sense. And the second thing is also that the anti-canonical degree is the same as a degree in the projective embedding. Okay, so we want to prove it's super rigid. We go by contradiction. So assume that there exists a birational map phi from X to some X prime, some Maury-Faber space, and phi is not an isomorphism. Okay. So I can write, after fixing an embedding and everything, you can write phi as being the map defined by some linear system. And this linear system is contained inside minus r kx, which by the way, this is the same as Ox of r. I'm going to pick D inside H to be a general element in the linear system. And now we can use another Fano inequality. Implies that if I look at the pair X, 1 over RD, this is not canonical. So there is an exception divisor with low discrepancy. Low discrepancy less or equal than 1, less than 1. On the other hand, the first bound or multiplicity of Publikov implies that the multiplicity of D at any curve is bounded by R. And this implies that the pair is canonical in dimension 1, i.e. away from a finite set. And here I'm using the bound that I can only sketch the proof on multiplicity. If the pair is not canonical, then the multiplicity has to be, say along a curve, then the multiplicity has to be at least is greater than 1, and then multiplied by R, I get a contradiction. So the conclusion of these two observations is that there exists a divisor E, an exception divisor over X, such that two things. The center inside X of E is a point. And the low discrepancy of X, 1 over RD is less than 1. Okay, so such a divisor, the existence of a divisor with low discrepancy less than 1 is a way of saying that the pair is not canonical. This is an exception divisor. But then using public of bound, we can ensure that the center has to be a point. And this is important for the next step. So what I'm going to do is going to let S inside X containing P to be what? A general hyperplane section. Through P. So in particular, S is what? As degree of S is 4. So it's a surface in P3 of degree 4. The only thing I care really is about the degree. Okay. So you notice that the order along E of S is at least 1 because S contains the center of E. So when I pull back S, it will vanish along the divisor E. So I see that if I look at the low discrepancy of the pair X, 1 over RD, to which I add S, before was less than 1, but now I'm subtracting a quantity which is at least 1, so I get something which is less than 0. Okay. But now you can use inversion of adjunction. Implies that the resistance divisor F.
Tommaso,
Yes.
sorry, can you say again why the discrepancy drops and becomes negative?
Yes. Let me actually add one step here. So this, by definition, is, if you just look at the definition, the low discrepancy of a pair is the low discrepancy over X of the canonical relative canonical divisor plus 1 minus the order of the scheme of the divisor. So if when I add S, it's the same thing as looking at what we had before and subtracting the order along E of S. But this number is at least 1.
Okay, okay.
And now, so you get something which becomes 0. So it drops by 1. By adding S in the pair, I drop the low discrepancy by 1. Okay. So.
Sorry.
Yes.
Doesn't you miss a minor or equal to 0?
Yeah. I was going to make a comment about that. So
okay.
let me first write the statement and then explain why I can argue that.
Okay.
So I want to apply inversion of adjunction and say that f, there is a divisor f over s with center p in S, such that, and now we have the log discrepancy at f of s 1 over r d restricted to s less than 0. You say correctly, when I prove inversion of adjunction, I had weak inequalities. I have less or equal than 0. So the conclusion here is that we get only less or equal than 0. So what I'm going to do here is that, okay, say I have a less or equal than 0 here. But because I have some room here, I can change these coefficients a tiny bit. I can make the coefficient a little bit smaller, use a weak inequality, conclude I have an weak inequality with a smaller coefficient, and then bump it up again, and I get a strict inequality. Yeah, you need to do that, actually. You cannot apply inversion adjunction like this without worrying about what I said. But I'm not going to write it. So the application is correct, but requires this little step of moving a little bit away. In the note is written more precisely. And so this step is written also in the notes. Okay, so now we're almost done, almost ready to finish. Okay, so now we want to cut down to a scheme. So recall that this one is a movable linear system, which means the base locus of H has codimension at least 2. So what I'm going to do is I'm going to pick up another general divisor. So I have D, and I'm going to pick up a D prime in H. So I'm going to pick up 2 general divisors, 2 general elements in a system. And I'm going to work with Z to be the intersection. Oh, sorry, inside X. So this is a complete intersection of codimension 2 in X. And the point here is that the order along E of Z is the same as the order along E of D. This is just another way of saying that if I have an ideal in a ring, inside a ring, and I compute the evaluation of an ideal A, it's the same evaluation of element F, where F is in A as a general element. It's like a general linear combination of a set of generators. So I can repeat everything I did before, or I can make this remark on S directly, and what we get at the end is that I have a similar condition now on a pair, which is a pair of this form. Okay. So this is what we get at the end. But what is interesting here? What is interesting here is that now this one is a zero-dimensional scheme. So another way of saying this is that if I look at the ideal of 0 restricted to S in the local ring at the point P, this is an MSP primary ideal. So we are now in the setting where I can apply the theorem that we just proved. And by the previous theorem, what we know is that the sign multiplicity of this ideal, which by definition is the sign multiplicity of S along this scheme 0 restricted to S at the point P. The notation is heavy, but that's what it is the least what? The dimension, which is now 2 square, divided by the log-canonical threshold square. But the log-canonical threshold of this pair maybe I should say, this means that the log-canonical threshold of the pair is of the pair, maybe write this with pair I'm talking about. T is less than 1 over R. So when you put it together, so this becomes strictly larger than 4 R squared. On the other hand, Bezout implies that the same number, this multiplicity, is no larger than the degree of what? The degree of S, which is 4, times the degree of the equations cutting Z. There are two equations, so it's R squared. So you get a contradiction. If you compare these two, you're going to get a contradiction. And that's the proof. Now, so again, so what we did is that we have this birational map. There's a base locus. The base locus is singular, but a notified inequality. How much? Well, using imagine of a junction, cut it down to a surface, I get these singularities in terms of some log-canonical threshold. And now I translate this into a conditional multiplicity. And I say the multiplicity is very large. But now remember that everything is, I have full control of the equation cutting out these things. So I know the multiplicity cannot exceed the corresponding Bezout number. And I get contradiction. So the way it works here is that I have two folds here. This one is 2 squared. This one is the degree of X. So it works in dimension 4, in dimension 3, because the degree matches exactly this 2 squared. If I try to now to look at higher dimension, we need to do something different, because I need to look at things of high degree. Okay, so I think that this is what I want to say today. And the next lecture, we're going to look at a high dimensional setting and see what we need to do there. Any questions?
No. Io forse fra un mese ce la faccio, però bellissimo, guarda, veramente
Molto elegante.
Però sì, sì, esatto, è cioè, da rivedere tutto insieme, comunque è bellissimo, è in mezzo. Ah, sorry, you put together all the things, wonderful, wonderful. Thank you so much, really.
No problem.
Maybe in 1 month I will understand something.
It takes a while to
yeah, especially log threshold, log discrepancies and so on, but I will check everything.
Okay, should I stop the video maybe?
So Tommaso,
Sì.
what happens for singular quartics? So for instance, a quartic with a single double point.
Yes, yes. So, okay, let me answer the question. So if you ever see a double point on a quartic, then it cannot be birationally super rigid for a simple reason that the projection from the singular point will give this birational involution.
Yes.
But you can still ask whether it's birationally rigid, which is a slightly weaker notion in which you allow these kind of involutions. And so Corti and Mella, they worked on this. So Mella has a paper, Max has a paper called Importance of Being Q factorial, if I remember well. So a key condition here is Q factoriality of the quartic threefold, which depends on how many double points you have now, I think.
Yes.
And so I will have to look it up again. I think that so if it's Q factorial, then you can still prove.
So if you have only less than 4 double points, then
correct. Something like that. So if there's few points, it's still Q factorial, and beyond that point, then it's not. So birational rigidity, so you allow some involutions, then is related to these double points. So it's related to the Q factoriality. That's, I think, what they prove in the end, and maybe this Petrov Mella.
I see. Very good.
But I would like to look it up again. I looked at this a long time ago.
Okay.
Yeah, so it means, yeah. But then if the dimension increases, then you can start allowing more singularities. There are statements in this direction that one can make.
You can start allowing terminal singularities, right?
It's a bit more complicated, actually. So, so there is a, well, if you just look at ordinary singular points, so these are say for simplicity of discussion, just talk about isolated singularities. So if you just look at isolated singularity, then you assume that the exception divisor, the blow up, is smooth. Or something about the tangent cone is a cone of a smooth variety.
Yes.
So these are the ordinary, I think, maybe quasi, what's the terminology? Quasi-homogeneous singularities, these are called. So in that case, the idea is that the larger the dimension and degree of the equation of the upper surface, it's still a final become of index 1. The larger the dimension, the more singular you can allow the upper surface to be. And then at a certain point, as soon as you can prove statements of birational rigidity, super rigidity, then it doesn't matter how many points you have. These are more subtle information. And then if you want to look at other type of singularities, the right condition, and I wrote a paper about this, that's why actually I know these subtleties. So the right condition, at least for my proof to work, is some condition that afterwards I found in Tessier papers, I think. So what you need to do is that you need to look at the Jacobian ideal or the variety. And you look at you ask, you want to compare to the power of the maximal ideal. Essentially, you want to condition the measure how many powers of the maximal ideal lie in the integral closure of the Jacobian or the variety, I think, something like that. So this gives another way of looking at singularities. And somehow that turned out to be a good way of understanding birational rigidity questions. Yeah.
So next week we are going to higher dimension.
Next week we're going to go to higher dimension, and then we're going to switch to this other topic on the formation of rationality.
Okay.
Yeah.
Okay, thanks.
Okay. Let me maybe stop the recording here.